Vale, bueno a todos.
50 people.
Vale, vamos a empezar con la charla de hoy. Gracias por venir a todos. No os voy a contar nada nuevo, la mayoría ya habéis venido varias veces, así que la charla de hoy va a ser en inglés, solo si la presento en castellano, porque por lo visto es mayoría, pero va a ser en inglés, ¿vale? La presento de los chicos de la boda, se han guardado un huevo, mola un montón, así que preguntarles como si hubiera banana, porque el tema es muy interesante, ¿vale? Entonces, a ver. Sí, vale. Tenéis ahí el hashtag, se va a grabar la charla, pues la queréis compartir después, se va a poner en directo también, voy a tirarle el directo para que lo compartáis, pues si tenéis compañeros que no han podido venir, que siempre pasa y tal. Así que nada, hemos hecho un gran esfuerzo para que se pueda grabar y todo esto, así que espero que lo pueda disfrutar más gente también. Entonces,
bueno, pues nada, buenas tardes, bienvenidos a todos. Nosotros somos Vidrin, somos una agencia de viajes online, tenemos 5 brands, estamos en todo el mundo y bueno, aquí el equipo de nativos, que estamos entre Madrid y Barcelona, estamos, bueno, aquí tenemos el enlace de que estamos contratando, ¿vale? Somos un equipo en el que intentamos utilizar clean code, buenas prácticas y la verdad que si alguien tiene ganas de trabajar en una empresa en la que intentamos utilizar las últimas tecnologías y se trabaja bastante bien, aunque esté mal que lo diga, pues nada, bienvenido al equipo. Y luego a las 8 cuando terminemos tendremos cerveza y pizza, de que no salgáis corriendo, no vayáis muy rápido y disfrutar de la charla que tiene una pinta estupenda.
vale.
Bueno, chicos. Vale. Bueno, hola a todos, yo soy Xavi Rigao y él es Paul Blondel de Liverpool y yo soy de aquí de Barcelona. La charla de hoy va a ser de Android Things y como Paul es inglés, pues la vamos a dar en inglés. Supongo que más o menos la gente controla. Sí. So, yeah.
So we'll do it in English. Sorry.
Oh, yeah, and we both work for Novoda.
Yeah.
So, you.
Okay, so who has done any IoT stuff? Nobody? And any Android thing stuff or Arduino? Okay, cool. So for the rest, it's an introduction. And for you guys, it's an introduction. So Android Things is another flavor of Android aimed at small technologies and IoT platforms. So Android at the moment comes on mobile, on Wear, tablets, in your car, and now it's the IoT platform. And the idea of Android Things is it's aimed at powerful IoT applications. So it's not small little single sensors. It's for accumulating data or bigger processing power or taking data from cameras and being able to adapt it and infer things from it. So it's not aimed at the whole IoT spectrum, it's aimed at the higher computationally expensive IoT stuff. So these are some examples are like things like security systems or an interactive ad banner or a vending machine. So Android Things is a full stack Android implementation, and this means that it's like Android on your phone, except the only app that's running is your own. And so Google will manage the framework for you, and you create your application, and Google create a board support package. So when you have your Android board, it'll get flashed with the whole Android system, and Google will manage all of that for you, and you just put your APK into it, and that's how you get Android Things application. So you have the IoT developer console, and here is where you upload your APK, and then you would download a system image, and with that system image you flash it to your board, and that's how you have an Android Things board. You get automatic secure updates if you use the IoT console. So this means that whenever vulnerabilities are found in Linux or the Android framework, then they are automatically pushed to your IoT devices. And it also means if someone has an Android Things device, but that manufacturer maybe has gone out of business or has stopped pushing their own updates, Google with Android will still push security updates for that device. It has signed images and verified boot. So these are things that Google do for you on the Android side. This means that every time your IoT device updates with Android, it will update one partition whilst running on the other partition, meaning it will check that it's updated correctly and booted into the new partition. So it will always roll back if anything goes wrong in the update process. So basically what Google are trying to say is they're trying to take all the hard work away for you, and you just write your Android application and it works. So this is what an IoT board looks like if you're practicing development for Android things. So here, this little square here is called the system on a module. So this is your SOM architecture. And so this means that this is the core of your system. This has the processor, the RAM, the CPU, and everything, the Wi-Fi chip, everything that's needed to make your system. And then this is your bigger breakout board, so it allows you to have like USB, micro connections, GPIO connections. And so if you went to production with one of these things, you would take the SOM like this, and then if you only needed 4 GPIO, you'd take something like that. You'd end up with a board that's 5 times smaller than that. So these big boards are just for development. You have to think if you went to production with something, you can really squash them smaller. Yeah, and the BSP here, so that's your board support package. So that means that your APK will run on this hardware and this hardware, and you don't have to worry about it. Google do the board support package, so they make sure that all the drivers and all the interactions work no matter what the underlying board is. So this one's an Intel one and this one's an NXP, and you can have the Raspberry Pi as well. So if you've seen this diagram before, this is an outline of AOSP, so the Android open source project. And this is what Android looks like when it's shipped to your phone. So you have all your applications like the launcher application, your phone book, calendar, and browser and stuff at the top. And then the application framework is your activities, your system UI, the home bar at the bottom, the status bar, your notifications and all of that. And then this sits on top of more of the Android runtime and the libraries with, I don't know if anyone knows, like the SQLite or HAL that's used, and then that all runs on top of Linux. And so for Android things, they stripped out all of the applications from AOSP, so there's no launcher, or there's no contacts or anything which you expect. And then in the application framework, they've got rid of content providers, they've got rid of the system UI, they've got rid of the status bar. So this means when Android runs, it's just your application that runs. You can't press home and go back to the launcher, or you can't see a little bar across the bottom. It's literally just you have a full screen application and you can do whatever you want and you control the whole device. So that way they've squashed AOSP down to run on IoT devices, but as you can see, the rest of it is all Android underneath. So that means you have all the power and leverage that Android gives you. And so from the last slide, you saw that it got rid of the status bar and all the UI elements. So this means that displays are optional. So you really need to consider alternative UIs for this. So like the Google Home, where it has a voice UI that you speak to it, or like Fire TV that has a remote control that you control the UI with. So you have to remember that you might not have a display, but you can have one if you want one. So everything is in the system. The linear layouts are still there, recycler view is still there. You can still use the support framework if you want, but they're optional, so you don't have to. But it means if you do have an application and you set content view, if you run that on an Android Things board, it'll actually work if you plug in a display. So Charlie's going to go through some of the low-level protocols to explain how you'd actually get started with Android Things.
So Android Things has Java APIs to communicate with these protocols, which are GPIO, PWM, SPI, I2C, and UART. So if you've done any embedded systems engineering before or anything related to IoT, then you might know them. But if you don't, then don't worry too much, because Android Things abstracts you from most of the implementation details. So you still have to know how the protocol works, but you don't have to know like every single detail of the protocol. And we'll discuss the protocols in detail now. Oh, and by the way, since the release of Android Things Preview 2, which was last February, Google have released native support for the peripheral I/O. So that means you can write a native application using the NDK with C++ and communicate with these protocols using C code, essentially. Cool. So the first protocol is GPIO, which stands for General Purpose Input Output. So this is the simplest way of communicating with peripheral. Basically, you can have, it only needs one line, and you can read values from that line and write values to that line. When you read 1 or a high, that means that the peripheral is emitting data, or you can also write that 1 or 0, which means either high or low. So that's used to, for example, if you imagine a movement sensor, if it detects movement, then you would read from the GPIO pin, and it would emit a 1 when it reads the sense, like the movement in front of it, and it would emit 0 if there is no movement. And in the real world, you can imagine a smart light bulb, for example. So if you wanted to turn that on, you would write 1 to the, or high to the GPIO pin, and then it would turn on the LED. And then when you write 0 or low, it would turn it off. So the next one is PWM, or pulse width modulation. So this is a bit more complex because it lets you write a wider variety, or a wider range of values, not just 1 and 0. So this can be used with more complex devices that I can explain in a bit. The main idea of PWM is that you don't just write 1 and 0, and you can only use it to write data, you cannot use it to read data. So the way this works is that you have to set the frequency that defines how often you're gonna be repeating the pulse, as you can see in the diagram, and then you define the duty cycle, which is the width of that pulse for the frequency window. So that's the value we're going to be writing to the port. So as you can see, if you send like a really tiny cycle, then it's going to read it at 0%. Then if you do a bit more, it can be 25% and so on. So you can write more values than just 1 and 0, or they can be interpreted as more values. So examples of this could be an LED strip. So imagine you have a LED strip that only has one color. So you could set a value of 25% duty cycle, and then that would set the brightness of all the LEDs in the strip to 25% brightness. And then in the real world, if you imagine a door lock with a servo motor in it, then you would use PWM to be able to move the servo motor to unlock the lock when the user like types in the right passcode and stuff. So next protocol is SPI, also known as Serial Peripheral Interface. So this one is a bit more complex. It also needs more lines than GPIO and PWM. So this one needs data and clock. So the clock is used to synchronize between the two devices. So SPI uses a master and slave communication. So you can imagine the master being the Android Things board, or a Raspberry Pi in this case, for example. And then each slave is each peripheral you want to talk to. And then if you have to talk to more than one slave at a time, then you're going to need extra lines that are called chip select lines. So that means when you want to send data to a slave, then you're going to have to use the clock, the data you want to send, and also select or send a high value to the line that addresses a slave that you want to talk to. And the protocol itself in SPI is not set in stone, so it will depend on which peripheral you're using. So you're going to have to read the documentation for each peripheral. So some examples can be an RGB LED strip. So this is different from the previous one because you can address each LED individually. So that means you would use SPI and you would send a byte array, and each byte can be the RGB value for each LED, and then that means you could set different colors to each LED in the strip. And then if you imagine in a real world, you would have for example, a weather station with multiple sensors. So in this case, each sensor can be a slave, and then you would have your Android Things board talking to or reading values from each sensor, and then you would have to have chip select lines to select which sensor you're reading from at any time. So next one is a bit more complicated, which is I2C, integrated circuit. So this one can look a bit similar to SPI because it also needs two lines, clock and data, and it also uses master and slave architecture. But it's different because the slave uses each slave is represented with a different address. So it's more scalable than SPI because you don't need to add new lines to talk to multiple slaves. You just need one line, and then you pass in what address of the slave that you're trying to read from or write to. And then I2C uses data frames that are structured, and these data frames include the data you're sending as well as acknowledge bits that are used to detect errors in the protocol. So you don't have to worry about that when you're implementing this protocol. And then example of this could be a temperature sensor. So you would use I2C to read the temperature values from the sensor or from an electronic compass, for example. And then if you imagine in the real world, like a smart alarm clock, then you could use I2C to write the values for the LCD display to display the time. But also you could do something smart, and like if imagine that smart alarm had an accelerometer, then you could read the values from the accelerometer to figure out if the user is already awake, because you could figure out if they've picked up the alarm to like turn it off and stuff. And then those two slaves, the LCD display and the accelerometer, would be selected using the addresses I mentioned earlier. The last protocol is UART. So while SPI and I2C are synchronous protocols, UART is asynchronous, which means it doesn't use a clock line to communicate between the two devices or more than two devices. So in this case, instead of clock lines, the synchronism has to be built in the protocol itself. So UART typically consists of two lines, data in and data out. So that means there's no notion of master and slave. There's just two regular devices that are at the same level, and then you have to figure out the communication between the two. So in the real world, typical examples of UART are GPS and XB radios and similar type of radios. And then in a real world example, you can imagine a small printer, like a receipt printer in a shop or a restaurant. Then you would use UART to send the values or the data, the pixels that you're trying to print in the printer. Cool. So now that we know the supported protocols in Android Things, let's see an example of how to use one of them. So in this case, we're gonna use SPI to light up an LED in an LED strip. So for the ones that are not familiar with Android, sorry, but this is not gonna be too complicated. So we start with a regular activity. So for Android Things, we don't have to extend any special activity, as Paul was saying. We just use the standard Android framework. Then the first thing we're going to need is we're going to have to get an instance of the Peripheral Manager service, which is the class we use to communicate with the peripherals that you have. And it also lets us query the current board, what are the ports that it supports and all the buses. So for example, the Raspberry Pi, I think it has 2 SPI buses or ports, but then another board can only have one, or may only have one. So you would use the Peripheral Manager service to get that information. So now that we have the Peripheral Manager service, we can go ahead and open a connection to that bus. So the service gives us these open something methods. So in this case, we use open SPI device, and we have to pass in a device name. And this device name will vary depending on the board you're using. So again, you're going to have to check the documentation. And then everything in Android things or everything that has to do with peripheral communication can throw an exception, an IO exception. So you want to make sure you catch that and handle that correctly. And then for every open operation, you want to make sure you use the close method on the given device to make sure you don't leave that resource hanging. If you forget to close the bus, that means you're not gonna be able to use it later on until you restart your device. So that can be quite annoying, because then if you relaunch the application and if you forget to close it and then relaunch the application, you'll get an exception because that's already open. So always make sure you match the open method call with a close method call on destroy or whatever it's necessary. Okay, so the next step is configure the device. So again, this will depend on which peripheral you're using. In our case, we want to use SPI mode 0, which means clock signal idles low and data is transferred on the leading clock edge. And I've got this written here because I can never remember. And then in our case, the LED strip supports multiple frequencies, so we can pick one such as 1 megahertz, and then we try to use 8 bits per word, which is essentially one byte at a time to communicate. So now we can create our handler. So we're going to use this handler to send the commands to the LED strip. So this means we're going to make our code asynchronous, but still being on the main thread. So we're going to take advantage of the Android event queue mechanism instead of using multi-threading, for example. As a best practice, we'll start communicating in the onStart method of the activity, and then we want to make sure we stop or remove the callbacks to the handler in onStop. This will avoid the sending unnecessary commands when the activity is not running anymore. And then the last step is create the runnable that will actually toggle the LED on and off. So we just create the runnable, and then this is the most important line. So we have to write on the device, we have to write those bytes that will trigger the LEDs on and off. So in this case, we are sending a byte array of 3 values, R, G, and B, and this will turn it on with some random values. If you can figure out what is 1, 2, 3 in hex, then and then you just post it every second, and that will work. So now you might say that was a lot of code only to turn on and off one LED. So Google have come up with this idea of drivers. So I can explain you what it is. So there's 2 types of drivers, also known as user drivers. The first one is driver libraries, and the other one is input drivers, and they are slightly different. So driver libraries are reusable components that you can develop, or people can develop for Android things, and then they can publish them. They usually wrap, or they abstract you from the specifics of the protocol, and they are used to read values and write to a specific peripheral. So you can think of user drivers as a thin layer of abstraction, so that you don't have to worry about, like, what I was saying about the frequency or the SPI mode. Oh, and you can find drivers on GitHub very easily. So in this case, for example, this is what a user driver for the LED strip could look like. So instead of having 30 lines of code that I showed you earlier, you can have 2 lines of code. First one being creating the driver, passing in a device name, which is the SPI bus again. And if you're using different LED strips, maybe you want to change the order of the RGB bytes. And then just write to it with the colors you want. So this, as you can see, this makes it a lot easier than having to know all the specific details of communicating. So the other type of drivers are input drivers. So the idea of this is that you can register your input driver in the framework, and then you could generate input events, and then Android can gather all these events and send them to the Android event pipeline so that another application can pick them up. So in this case, it means, because what we said earlier, you cannot have two activities running in the same Android things board, then you're going to have to use services to feed those events to the framework, and then another foreground activity can read those values. And so there's different type of drivers that Android Things supports, that input drivers. GPS, HID, which stands for Human Interface Device. So this could be like trackpads, touchpads, mice, joysticks, keyboards, anything that has like some sort of buttons. And then you have also sensors such as temperature, accelerometer, humidity, whatever. So an example of this could be, imagine you have a XB GPS module. We could have a package installed in our Android Things board, and that package has full service. So full service can read values from the GPS module. Then full service registers in the framework as an input, GPS input driver. And then someone else, in this case bar activity, if they register for location updates, then they'll get those GPS updates as well as whatever else there is. So you can imagine you can have like 10 of these with different modules, and then bar doesn't care. They'll just get GPS updates, and it doesn't care what's in this side. And so in this case, we can have full service and bar activity be from different applications, different packages. So an example of that could be, in this case, we want to build a simple keyboard. So the first thing we have to do is we have to use the input driver builder, and we tell it which type of input driver we're trying to build. So in this case, it's button because our keyboard will have buttons. Then we have to give it a name and a version. So this is in case you make changes to that driver, then the framework can handle it correctly. And then we tell it which keys our driver can emit. Then we build it. And then we have to get an instance of the user driver manager, and then we can register this input driver. So from now on, we can already emit events, and the framework will already pick those events and forward them to whoever is listening to key events. So this is what we do here. So we create a new key event, which is the action down. So you're pressing the key, and the key code is T. So we're going to send the letter T down event. And then the emit line is the one that actually triggers that sending. So as you can see, there's not many details in here because the framework takes care of all of that for you. Cool. So now we talked about the peripheral I/O and all the drivers that Android Things supports. So now we can move on to best practices essentially, and how to build the best IoT apps.
So Xavi showed you how to use the different APIs that are available on Android Things, and once you've got this down, you can talk to the different peripherals. You're going to be making an Android application, and you want to be following like your clean code, clean architecture best practices. Make sure you've got separation concerns. So we've done a few applications, and we want to share what these conventions are for us. So talking about all the different peripherals, like Xavi gave examples of, we split them down into two different sections. So we have active peripherals and we have passive peripherals. And the idea are active ones are things that do their own thing once they have power, and passive peripherals are ones where they're waiting for something to activate them, like a button. And so we can split these down again into output and input peripherals. So output peripherals would be like a speaker, a motor, an LED display, a segment display. And input peripherals would be like buttons, temperature sensor, or a lock or something. So if we describe what an input peripheral is, another word for an input peripheral is a sensor. So this can measure a physical property or respond to it. So this is a description of a temperature gauge or a monitor or a button. And then output peripherals can also be called actuators. So an actuator is something like an LED screen or electric motor. and it's responsible for moving or controlling something in the physical environment. So if we agree on these terms for input, output, sensors, and actuators, it means we can have good naming conventions when it comes to your code. So here we have a motion detector, which we are calling a motion sensor, and we have a speaker, which is our piezo sound. And so these are some examples that we have in our code base. And it means that when you have multiple developers, you can all agree on your naming conventions and understand what lives where and what has what responsibility. So this means you've got clarity when reading the code. So you know if this is a sensor, then it's going to be bringing data in, and if it's an actuator, then you know it's going to be changing or moving something in the outside world. And clarity when searching. So if you know that there's a problem with your application with output, then you can search in your actuators. So this leads to better team discussions. Everyone on the team understands what an actuator or a sensor is. Everyone is on the same page when you're having a discussion, and there's no arguments around how a sensor works or how an actuator does something. So that's a simple way to do naming conventions. And we've also managed to agree together on our package structure. So this is a bit small, but maybe you can read this. So this is an example of grouping by type. So you have all your activities together, all your models together, all your peripherals together, and your services together. And it will quickly allow you to find all the code of one type. So if you want an activity, you go look in the activity package. And another example here is grouping by protocol. So grouping by type is still grouping by protocol, but there's no protocols in normal Android. So protocols are like GPIO, PWM, I2C, I2C. And so you have all your GPIO, like your barcode scanner, your sensors, and your price input sensors. You have them all in one package. And so the advantages of this is it's tidy and everything is a place, and there's a place for everything. You know that your GPIO sensors are in your GPIO package. Well, hopefully from this side, you can see that the downsides outweigh the advantages here. So you don't want to always remember what protocol your sensor or actuator is using. And there's a lot of context switching because you'll change code in the activity, then you'll change code in the GPIO package, and then you'll go to the service package and change something else. And it increases your package tangle index. The package tangle index is like a KPI for monitoring code quality. So if you have things like check style or sonar running on your project, then this is a static analysis tool like that. So package tangle index tells you that all these classes in this package always communicate with these classes in this package. And the more tangled your code is, the harder it is to make changes and to understand what's going on and get through your code. So our alternative solution is to group by domain concepts. So in the last three examples, these are all the same classes. The only things that are changing is the package structure. So here we're grouping by login, shopping basket, checkout, and receipt. And so this way, you can actually understand what the application is doing, and if you're working in one section, it's all going to be in the same place. So it's easier to remember where to look. So if you're working on login, if someone says we need a remember me feature in the login, you know to go look in the login package, and you're like, oh yeah, we use these sensors and these actuators for login. All the code is in the same place, so if you work on login, you're in the login package, and there's less chance of conflicting changes. So the bigger your team, the more chance people are going to be working in the same place. If you're working on the PinPad login and someone else is working on the infrared login, then if you were doing that all in GPIO package, there's chance you're going to hit each other's code. But if someone's working on login and someone's working on basket, then you're working in two separate, distinct places, which avoids more conflicts. So that's another convention for package naming convention. And then the final one is for peripherals and MVP. So if you use MVP, then don't listen for 10 seconds. But a quick explanation of what MVP is MVP stands for Model View Controller. So the model is your business logic and the brains of your application. The view is your UI and how you display and how the user interacts. And then you have a presenter that sits in the middle. So the presenter coordinates between the model and the view. So the presenter gets the information out of the model and pushes it onto the view and says to the view, show me this. So if we take Model View Presenter and think about IoT and Android things, the model is your business logic, and if we remember the definition of a sensor, it detects or measures a physical property and responds to it. And so this means that Sensors are all about input and bringing things into your application. So your sensors should live in your model because that's where data is going in and that's where you need that data. So if you had like a temperature sensor that's giving you degrees Celsius, then your model is the one that needs to know those degrees Celsius to be able to calculate something to pass it on. And then for the view, which is user interface, this is usually your actuators. So for imagine what an actuator is, it's about sharing something, moving, reacting. So this is what your user interface is. So for example, like a segment display or a motor that moves, that's part of your user interface and that's how you move things around. So if you have something that's named an actuator, it's usually going to live in your view. So having a separation of sensors in your model and actuators in your view allows for more clean code, more maintainability, a nicer separation of concerns. Things live on this side or they live on this side. Faster development through agreed standards. So if you're doing pull requests or code reviews, all the developers on the team will agree, yeah, that's a sensor. It obviously should be in the model, or that's an actuator. It clearly lives in the view. Faster debugging, because if you see there's a sensor in your view, then you know there's a problem. And clarity and discussion around class responsibilities. If you have a class that pulls in the temperature and then also tries to display that temperature on the screen, then you know it's doing two things, and you should split that up between your model and your view. So that's our third convention for understanding IoT in terms of Android, because Android is a really powerful platform, and you already have a lot of knowledge that's usable in the IoT space. You just have to pull in the different things. So now we're going to talk about best practices in testing.
So so we'll start with driver testing. So sorry, I'm a bit lost.
I gave him the wrong intro. That's not
yeah, exactly. I'm confused now. So since the driver is gonna have to make use of the framework classes, which is like the SPI device I showed earlier, or the UART device, whatever. So that means what we're gonna have to do for our driver is we're gonna have to test based on behavior. We cannot test inputs and outputs, or it's not that easy at least to figure out. So yeah, we're gonna have to mock the framework classes, and then hopefully we can extract some collaborator classes from our drivers so that you can test those separately, and then you have some reusable code. So a practical example would be, if we start from the top level, we imagine we have a light strip actuator which will like flash red lights if the user has done something wrong to show that there is something they have to fix. Then we would have our actuator, which is the subject under test, and then we want to mock the driver, which is the WS2801, which is in this case is the one that controls the LED strip. And then a simple test could be to call the show error method on the actuator, and then we verify on the mock object that we are writing the red color on it. So now if we move on to the next level, which would be the device, the driver itself. In this case, the driver talks directly to the framework classes, which in this case is the SPI device. So we have our subject under test, which is the driver, and then we are mocking the SPI device. So two simple examples could be making sure we're configuring the bus properly. So if we create a new instance of the driver, the 2801 driver, then we could assert that this is calling set frequency with 1 megahertz, which is the frequency we need to talk to the LED display, or LED strip, sorry. Or another example could be if we have a list of colors that we're trying to write to the LED strip, then when we call the write method on the driver, then it is delegating that method call, or it is forwarding that method call to the framework device with some byte array. Now imagine that we had some code in the WS2801 driver that gives us a byte array with the RGB values or RGB bytes in the right order, depending on the input parameter that we saw earlier, this one. Then if we want to separate that logic and make it more testable, then we could, for example, extract it in a static method or in a collaborator class, and then test that separately so that we are moving away the logic from the driver, because the driver only needs to talk to the framework classes. We don't need the driver also to have all this logic of knowing how to create that byte array. So in this case, we create this color unpacker. We create this static method, and then we could easily test it. So in this case, we're testing that we're sending the right order depending on the input parameter, which is the mode. And then we don't need to test this logic in the driver. And also, this class is now reusable. So if you had many LED strips with many drivers, then you could reuse this for all of them. Cool. So now that you know the best practices of writing your IoT applications, how to test them, how to name all the things, how to structure all your packages, and everything basically. We wanted to share some tips and tricks that we think can help you develop better IoT applications. So this is quite specific to Android things. So yeah, as I said earlier, don't forget to call the close method every time you're opening something. If you forget to close a bus, then you're going to leave that open forever until you reboot the device, which can take like 5 minutes because the Raspberry Pi is quite slow at booting. So you don't want to waste all that precious time. So always forget to close a bus. And then the other thing I wanted to say is in Android things, most of these supported boards use remote ADB. So that means you have to use the Android debug bridge over Wi-Fi instead of USB cable. So one thing that will help you in this case is if your router supports it, you can set a static IP address to the Android Things board so that you can connect always using the same IP address instead of a dynamic one. Or also another trick is using the default hostname, which is android.local. So again, if your router supports it and if you're in the same Wi-Fi network, then you can say ADB connect android.local and it will hopefully work. So this will save you time of looking up what's the IP address every time it changes. Oh, and then my last one is, since Android Thing doesn't have any UI, then if the app crashes, it's going to be quite annoying having to redeploy it. So you either, if you're using the IDE, if you're using Android Studio, you can easily redeploy, but otherwise you can have that command ready on the command line with your package name to make sure that when it crashes, you can relaunch it, because it doesn't reload automatically. And you hope, I mean, most likely you're not going to have a touch screen to redeploy the app. And there's no launcher anyway, so yeah, it won't work.
And so only one app can be active at a time. So what does that mean? It means, as I said before, the whole Android system is yours to install your APK, but you can actually install multiple APKs on Android, and you can on Android things as well. So this means only one is active. So when the device reboots, it'll start the active APK. And how it determines which one the active one is not known at the moment, but I think it's alphabetical, so it just picks the first alphabetical one. So if you have multiple apps installed on your Android Things board, it will just pick the first one alphabetically to start up when you power cycle the device. So this means you have to be careful, because if you're like us, hacking around with them, installing multiple things, trying different things out, you'll suddenly wonder, where's my app gone? Why is it installing this other version? So you have to remember to uninstall your old APKs when you finish with them. And so from that link there, we wrote a script that will just poll the device, find all the APKs on it, and uninstall all of them so you can start again. Each board has different pin or bus address names. So, you know, when you're looking at tutorials on the internet for Android things, everyone uses their own device. So I have a Raspberry Pi, someone could have an Intel Edison or an XP device. And the pin addresses that you use, like Xavi was explaining for GPIO and SPI and I2C, they're different for each board. So if you're following a tutorial online and wondering why it's not working, they might be explaining it for a different board. And there's also other tutorials out there, like the Google ones, that have a separate class, and that'll give you the pin addresses for every board, and it'll try and determine which board you're on and use it. So you just have to be careful when you're following online tutorials to understand it might not be the same hardware that they're explaining for you. You just have to tweak it a little bit. And then for threading as well, there's 3 different choices for threading. So because the whole Android system is yours. You can abuse it and run long-running operations on the main thread. So it's not like Android on the mobile. It won't time you out after with an ANR after a certain amount of time. You can just do all your work on the main thread. But obviously, if you're using an optional display, then that optional display is still refreshing on the main thread as well. So you don't want to do your hard work on the main thread because you'll get jank on your display. So then you can offload with async task or whatever threading mechanism you want to use. But you can also, like we did, just post back to the main thread and do it in an asynchronous way. So it's up to you. There's 3 different ways, and that link there takes you to a more in-depth discussion about what that is. So that's our talk about IoT and Android things. I hope it gives you a brief introduction into all of it. Is there any questions? Hopefully English questions.
Yeah. So about the opening and closing, that you said it a couple of times. I guess so the device is yours. So I understand that the problem is when you are developing, no? I mean, if you are starting and stopping the app.
Yeah. So the question is, when you're, we said that you have to always close anything that you open, and this can be a problem mainly when developing because otherwise the device is yours. Yeah, that's basically it. I mean, you're not gonna have. You're only gonna have, hopefully, in production, you're gonna have only your application running, so you don't have to worry too much about it. But I guess it's always a good practice to do anyway.
Yeah, if you write a more complex application, you might want to separate it. So if you're using the camera and you're using a temperature sensor, and then you're storing some secure credentials, you might want to split that up into 3 APKs so that if any of them become compromised, the hacker can only access the camera or only access the temperature sensor. He can't do everything. And so if you separate them, then and you control when they start and stop, then you might go through the lifecycle methods. So yeah, best practice, you should consider the lifecycle methods and open and close properly.
And then about the different activities, I guess this makes more sense if you are having some kind of UI. Because if it's like a router, for example, or a camera, probably it doesn't make sense to have different activities.
Yeah, exactly. You can do it all. So the question is, should you have multiple activities when developing an application? If you're just going to do something simple, can you just do it all in one activity? So yeah, you can all do it all in one activity. If you don't have a UI, then you could just throw it all into one. But I think if you're writing an IoT application that potentially has other usages, for example, we did one, just a game the other week that could run on a phone or run on an IoT device. And so that way we kept the multiple activities because that's how it worked on the phone. And then there was no harm to doing that on the IoT device. There was no downside, only potential benefits. So you could do it all in one activity, but you might be shooting yourself in the foot for later on.
Just a final question. When you talked about the devices and implementing them as a service, I seem to understand that you mean that they are separate packages in the sense of separated APKs, or you mean packages in Java sense of package?
So you mean in the input drivers?
Yes.
Yeah, so the question is, in the input drivers, we said that you could have different packages for the service and the activity. And so, yeah, it can be different Android packages, different APKs. As long as they are installed on the device and you use the service to emit the values or the events, then they can be separate APKs. Because the framework will add them to whatever that is already in place and feed them to whoever is listening.
So far there are a couple of 3 devices that can accept but in case there are more in the future, we have a way to test separate devices without having to have different physical devices. So if there's an emulator,
So
the question is,
if you have an application, you want to know if you want to work on every device.
Okay, I've got it.
They have to have it physically.
Okay, so the question is, if you want to test it working on multiple devices, do you need the physically or is there an emulator? So when you go to production with Android things, you are in full control of your hardware. So it's not like Android where the user will have a mobile phone and you're not sure what the hardware is and you have to account for that. You will say, we've developed on an NXP and we're using the NXP SOM. So we know exactly the addresses for all the GPIO chips and we actually would label them ourselves. You wouldn't expect it to work on any other hardware apart from the hardware you've written it for, because you will sell that piece of hardware. So yeah, you need to have it physically because there's no emulators for that. No.
Maybe it makes more sense in case of drivers that are not named maybe to work with just one device, but to focus on
yes, exactly. So in the case of testing drivers that potentially other developers will use, what Xavi had up on his slide where he had this simple driver that was 2 lines of code, in the constructor for that driver, it was still a parameter for the address. So you just make it configurable so that the developer that is using your driver can configure the options that can change per hardware.
Yeah. So you mentioned that you were doing this game that was for IoT and also running on mobile. So what about if I want that game to, the version in mobile, use content providers and things that are not in the native platform? How can I benefit from hexagonal architecture, things like that?
So the question is, if you do an app that works on mobile and IoT and then uses something that's not available on IoT but is on Android mobile, how do you account for that? Do you want to take it? I can do it.
Yeah, so ideally you would create your interfaces and you would have to name them something more abstract like repository or something, and then you would have an implementation for Android which uses a content provider, and then in Android things you would have a different implementation that does like maybe Firebase stuff or something that you can use in Android things.
And and the cool thing is, it's the same problem that you have on Android. If something's running on Lollipop or Marshmallow, you've still got to check. It's the same check. I can't do it off the top of my head. There's a one-liner to say, is this an IoT device?
And then this leads me to the next question. What is the name that you have used? Is not interactor, but the thing that displays or makes movements of the
Actuator.
Actuator. Don't you feel that the name is a bit weak in that scenario? Maybe displayer, maybe better.
So the question is, with the naming of sensor and actuator, does actuator suck as a word? I think I was looking through a lot of other IoT platforms and official Google documentation, and then the definition of an actuator is something that moves or affects the environment. So it definitely makes sense for motors and moving parts, and it's a little bit of a push to say your pixels move on the screen, but that's kind of how we went with it, yeah. But yeah, I can always change.
Did you consider using Java for like sensors that input values and like wrapping it in the observables and pushing the results to your app?
So the question is, did we consider using Java to push updates from the sensors to the UI or to your app? Yeah, I mean, you could do that, definitely. That's what we were saying. There's multiple threading choices. I think it would be interesting to do.
It's definitely possible because it's just Android, so all of those libraries that
Yeah.
don't have any UI components can be used. So you could do a functional component if you wanted. Yeah.
You'd have to implement, that layer to push the updates, but yeah.
You said you use this for production. Can you give us an example of what you built and which protocols you used?
So the question is, if you've used it for production, what protocols have you used, and that example? So
that's working right now.
Going to production, we haven't manufactured a board and installed it on it and sold anything. But we've built multiple games. So Xavi built his Simon Says game, which uses GPIO and
PWM.
So it has 4 buttons on it, and then it makes a sound through PWM. And then I've used UART and PWM as well for sound, and I2C for the screen, where we made like a piano game. So me and Atul, this other developer, it had a display, and on the screen it showed musical notes, and then on our keyboard we could copy the notes on the screen to play the sounds. It's kind of like Guitar Hero but for piano. But we haven't gone to production as in built a board and packaged it as a device to be able to sell. But there's a really great video from Google I/O called From Something to Production in Android Things, and it explains exactly the process, and it's really good to watch.
Yeah, the thing we did is we used a prototyping board to solder all the components there and connect it to a Raspberry Pi. So that was the closest we got.
What's the future you see on this? Because the phone everyone carries around, we updated it and it updates automatically. But if you have a company that comes and say, we're going to build these boards and you're going to do the app and the hardware, what happens when Android phone changes again? Like when there's an update, does it automatically update to get connected to the internet? You have to go hardware by hardware. Like what happens if you want to change the code or add a feature?
So the question is, if Android updates, how does Android Things keep up to date? So Android Things is based on Android O. It's going to be O.
Oh,
when it's shipped. And it's like I explained at the beginning. It's a system on a module architecture, and that means to run Android Things you have to have a Wi-Fi chip. So they're all going to be internet connected. So it's up to Google if they keep it up to date past O, but it'll just be like mobile. That if a new release, I'm sure they'll push a new framework release for Android Things as well.
How do you push a new app? Like if you change the app, you add something else. How do you push that into the hardware? So
there's an IoT console, which is exactly the same, not exactly the same, but the same theory as the app console or the app store. And yeah, so you upload your APK there, and then when your device goes to production, then Google manages the update of your devices, and it will push out APK updates to it, and it will do it, in a sensible manner. And I should have caveated at the beginning, Android Things is in developer preview at the moment, developer preview 4, so don't tell your client to make anything in production yet, but experiment with it and get to that point so that it's ready to go to production when Google says it's ready, because there's a lot of gotcha bugs in the release notes at the moment.
And also, in one of the podcasts, the Android Developer Backstage podcast, there's an episode about Android Things, and they mentioned that Android Things is fully CTS compliant. So that means it passes the same tests as any device that you can find on the shops.
What device we can choose for start?
For devices?
Intel Edison, Raspberry.
What developer boards?
Yeah, so the question is, what developer boards can you use to start playing with Android Things? So they keep adding new ones. So they started with the Raspberry Pi 3, the Intel Edison, and the NXP Pico, and now they're adding the Intel Joules, another NXP, or a couple more NXP devices, and
yeah, I think there's 5 available at the moment, and they are on developer.google.com/Android Things, and it tells you exactly there that those 5 devices are available.
Yeah, and then you can find the images on the website as well and flash the device.
What is the best for starting?
Oh, the best.
What's the best one? So,
Raspberry Pi.
No, but the developer advocates at Google say the NXP. And the NXP is really cool, but the Raspberry Pi is really cool as well. And the Raspberry Pi is like really easy to use. Everyone understands it, and it has loads of these peripherals that you can just plug together rather than having to solder anything. But the cool thing about this NXP board, which is brand new, is it's compatible with the Raspberry Pi's pinout. So that means all these hats that are available for the Raspberry Pi can now be used on the NXP. And the NXP is cheaper and has some other connections that the Raspberry Pi doesn't. So Google recommend the NXP.
Well, yeah, actually the NXP has USB debugging, so you don't have to fiddle with the
Yes,
Wi-Fi.
exactly. Yes.
Which is good. USB debugging, so you can debug where you...
Yeah, that's the one downside of the Raspberry Pi. When you first get it, flash it, you have to go find your router, plug your Raspberry Pi in, then ADB over LAN to your Raspberry Pi.
Well, you need a display to get...
Yeah. Oh yeah, and then you have to ADB to give it the Wi-Fi credentials, so that then your Raspberry Pi is on the Wi-Fi, and then you ADB over Wi-Fi to your Raspberry Pi to connect. There's a learning curve there with the Raspberry Pi, and you're right, the NXP, you just plug it in and it works like a phone. I remember there was a reason, yeah.
If you just connect one with Raspberry, for example, because you are connected to Raspberry Pi, and you plug the Raspberry, can you also reconnect automatically with NXP, so you have to implement on your own some threads to reconnect the...
To reconnect which?
You mean the ADB?
Yes.
So the question is, if you're debugging with a device like a Raspberry Pi over Wi-Fi, and you turn it off, then it will disconnect, and then is there any way to reconnect automatically when you turn it on? I think the answer is no by default. You can probably build a script that retries every 5 seconds or something. As long as the IP address doesn't change, or as long as you use the host name, then you should be able to write a script that keeps trying.
Okay, only every I don't know, every 5 seconds?
Yeah, so it takes...
It won't disconnect. It won't disconnect unless it power cycles.
Yeah.
It doesn't sporadically disconnect.
And it takes about a couple of, or 3 minutes to fully boot. So yeah, you don't have to do it every 5 seconds. You can do like every 15 or 20 or 30.
One question related also with the activities on the service that are running in the iOS device. So you said only one activity is running on multiple services, right? Okay, those services, do they belong to the activity that it's live, or can they belong to another application that is installed on the device?
So the question is, you have one activity running, but you can have multiple services running. Who owns the services? So yeah, you can have multiple APKs, and obviously you only have one foreground one that runs one activity. It's just like Android mobile. But if you have other background services that are registered in the manifest or programmatically registered, then they can be running. So you can have multiple services from different APKs, and then you have one activity.
But can you have any service that is running and it belongs to another application that
Yes.
it doesn't have the activity incorporated?
Yeah, exactly. So it's like on mobile, if you're writing a music playing application, you make a background service that plays the music, but then the user carries on using another app. So you can do that.
So if there is only one activity that is active, this means just one activity, no activities in foreground and background. So why do we need 4 or 6 life cycles on the activity?
Yeah, so I use the activity lifecycle when you're the only activity.
That's a little bit the question.
That was the question. So the question was, why use the activity lifecycle when?
Actually, not what to use. What will be good use cases for the other activities lifecycle callbacks, apart from on create and on destroy?
Well, like I was saying before, you can have multiple APKs installed. So if you could do something where you have a background service and it's monitoring for movement, and then when movement happens, it pushes its activity to the forefront. So then your other one would move to the background. So then you'd need to do stuff in on start and on stop, because this one is going away and this one is coming up.
But that would be on create and
destroy.
destroy.
Right?
So
Well, no, because it's Android, so it might not be destroyed because it's only going into the background, so it's going into your recent apps.
So you only have one activity on the foreground.
Yeah. So you'll get on pause and on resume, but technically it might not be on destroy.
Okay.
It's just like Android. All of the problems that you have with the life cycle that you have on Android, you have on Android things. You can ignore them all and see what happens. But you know what happens when you do that on mobile? So. Cool. We'll be in the pub as well, so you can ask more one-on-one questions, or bar, sorry, one-on-one questions if you're having a drink afterwards or whatever.
Bueno, chicos, pues ya son las fiestas aquí. Hoy os habéis entretenido a preguntas, me alegro. Y como dicen ellos, los tenéis por aquí para preguntarles. Gracias por venir.